Good evening, everyone. Welcome to our Astronomy on Tap February event. Thank you for joining us tonight. I am Dr. Cameron Hummels. I am a computational astrophysicist at Caltech, and I will be your MC for this evening's event. We've got a really cool event. It's a themed event tonight because this coincides with a 2-month-long scientific program at the Kavli Institute of Theoretical Physics on the topic of the circumgalactic medium, which, as the name suggests, is the gas around galaxies. So many of the leading researchers in the field are in that subdiscipline of the field are meeting these 2 months every day and talking about this topic and ways in which we can make progress on it. And we have two of the highlight personnel in this movement who are going to speak to us tonight about related topics. So let's see, a couple of quick announcements. So if this is your first time at Astronomy on Tap, welcome. This is a reasonably informal event consisting of two 15-ish minute presentations by scientists on science and Q&A following them. And then the latter half of the night, starting probably in about an hour, will be astronomy-themed pub trivia, which should be super fun. It's interactive. We've got a website that you can go to in a web browser or on your phone and answer the questions that we put out, and then it'll show up on our screen, and everyone can see how everyone else is voting and such, and it's super fun. Unfortunately, we don't have prizes, but pride is a prize enough, hopefully. We also, I can't speak for the other participants, but I'm having a beverage. Hopefully, perhaps you are as well. So it's a bit less formal. For more formal events, we have the Caltech Astronomy Stargazing lectures that happen once a month on Friday nights. Our next one will be in 2.5 weeks, and I don't yet know what the topic will be, but it'll be good. And I think it's going to be given by Kishala Day, one of the graduating PhD candidates in the department. So stay tuned to our website and social media and YouTube page, and we'll have updates on those sorts of things. And I think maybe, and we're going to start having virtual stargazing and some additional lab demos that aren't 2-hour-long live events to help provide more content to you guys about science and astronomy and so on and so forth. So if you have particular things that you'd like to see us do or questions that you'd like to have us answer, I encourage you to write in the chat or in the comment section of this, and hopefully we can try and brainstorm new ideas and ways in which we can spread the good word of science to everyone. Okay, so Jess and Zach, do you guys want to come back on? Hey, welcome, guys. You've got some wonderful backgrounds there. Jess, what's your background?
This is a snapshot from the illustrious TNG simulation made by Dylan Nelson, and it's the Cosmic Web.
Ooh, tell us what's the Cosmic Web, or are you going to talk about that in your talk?
I am, but it's kind of like the vast networks of filamentary gas that connects galaxies. It's the fabric of space-time, the largest structure in the known universe.
Okay, that's pretty awesome. That's good. Zach, what's going on in the back of your shot here?
Let's see here, I need to figure out which direction to scoot first. So this is Galactic Bloom, as it's called. It's an image I created with Alice Gurvich, a finishing graduate student at Northwestern, where I got my PhD. And it shows the paths taken throughout time of gas that may one day eventually form our sun. And you can see in particular this kind of like outward expansion and then inward fall. That's gas expanding as the universe expands, and then eventually, due to the force of gravity, collapsing back in. So there's more details. Cool. We can talk more about it later.
Yeah, no, super cool. Cool. And what, Jess, I see you have a beverage. What is your beverage?
This right now is a non-alcoholic beer from Spain, but after my talk, I've got my martini on the rocks ready to go.
There's no shame in having a non-alcoholic beverage. I was saying earlier that on these Monday nights I inadvertently drink a little bit too much, and then Tuesday morning is like, why, Cameron? Why did you do that on a Monday night? Why did you drink like 4 beers? That was a mistake. So smart, responsible. Zach, do you have a responsible beverage or an irresponsible beverage?
I have a responsible beverage of water, and I have an irresponsible beverage of mezcal, which we picked up when we were visiting my wife's family in Oaxaca a couple years back, and we've been slowly making our way through it.
Oh, sweet. I want to go to Oaxaca. That sounds awesome.
Yeah.
Cool. Well, yeah, for our audience, as I mentioned before, these two guests are two of the participants in our KITP, Kavli Institute of Theoretical Physics program on gaseous halos. I know everyone's like, gas, who cares about gas? But actually gas is super important in space. It's one of the major constituents. And I think we'll probably hear a bit about that from each of our speakers today. So I guess I'll start with our first speaker. Dr. Jessica Werk is a professor at the University of Washington in Seattle, and she studies the cosmic baryon cycle by observing matter on the smallest atomic scales as it courses through the vast spaces between galaxies. She uses spectrographs, such as the Cosmic Origins Spectrograph on the Hubble Space Telescope, to measure atomic transitions from gas billions of light years away. And the title of this talk was inspired by a conversation with astrophysicist Dr. Daniel Anglés-Alcázar, who summed up his work linked here by saying basically, we are all intergalactic immigrants. So she's also a trained opera singer, a mezzo-soprano, and has never been beaten in a wall-sitting competition, including by me. So wall-sitting, in case you don't know, is where it's, as the name suggests, like you have your back against the wall, but then your like hips are at a 90-degree angle and your knees are at a 90-degree angle. And it puts an enormous amount of stress like on your quads and your hip flexors. And I think I have pretty strong legs. I run a lot. And I was like, so people were bragging on Jess's behalf at one point. And so at a party, I tried to best her at wall sitting, and she destroyed me. She was unstoppable. She sat against the wall for like 20 minutes or something and wasn't even bothered by it. It was very impressive.
Winning is a state of mind.
All right, I'll let you win with this presentation. Do you want to share your screen?
All right.
Excellent. Looks great.
Okay, here we go. Well, thanks a lot for having me, and I am really excited to be here. So let's dive in. We've got 13.7 billion years of cosmic history to get through. So, as an astronomer, I basically consider all of us to be self-aware substructures in the cosmos, some of whom are drinking beer right now. Cheers. At the most basic level, our bodies are simply temporary collections of assorted atoms, many of which, it turns out, spent a long time drifting through intergalactic space billions of years ago. And that's the story I'm going to tell you this evening. So look, don't get me wrong. I'm not saying that we're aliens, but we're not aliens. All right, in this talk, I'm going to give you an overview of not only the origin of the atoms in your body, but also the long and sometimes really violent journey that they've endured over the last 13.7 billion years. But first, to understand this talk, there's going to be 3 things that we all need to understand. Let's get on the same page here. This is one of my favorite illustrations of the atom. And the first thing to maybe remind yourself of or know is that these atoms are the basic building blocks of all normal matter. Not dark matter, which is the subject of a whole different talk. We're talking about normal atomic baryonic matter. An atom is a nucleus of very tightly packed minute particles called protons and neutrons, which carry a net positive charge, surrounded by a cloud containing comparably tiny electrons that are actually really relatively far away, that carry a negative electrical charge, and they're in constant motion. And the attraction between the electrons and the nucleus is tremendously strong, much stronger than gravity. And if the nucleus of an oxygen atom were the size of a baseball, the electron cloud would lie a full football field away, which is crazy. Atoms are mostly empty space. That kind of blew my mind when I learned that. And so as electrons jump around in this electron cloud, it turns out that they're responsible for a lot of the energy we see radiated as light from the universe. And so these atomic processes happening are one of the main ways that astronomers study normal matter in the universe. All right, the second thing to understand involves appreciating the absolutely vast scales of the universe. Ultimately, my work involves trying to connect the very smallest scales, atoms, to structures on absolutely immense scales, the cosmic web. Okay, and astronomers are people too, and we get tired of writing zeros, and instead we talk about powers of 10. And powers of 10 allow us to just better compare sizes. And so the size scales of atoms compared to galaxies span more than 32 powers of 10. And so for reference, the size of you compared to the entire Earth is about 6 powers of 10. So yeah, so things are about to get a little crazy. All right, that's number 2. And finally, the third thing to understand is that not only are the size scales in the universe vast, the universe contains multitudes. And so this image here, the Hubble Deep Field, is one of my absolute favorite images of all time. It was observed over 10 consecutive days around Christmas in 1995, and they pointed this brand new telescope that they had just put up in space at a patch of empty sky near Ursa Major to see what they could see. Besides stars in the Milky Way and bright nearby nebulae and galaxies, what else was out there? And it was like a whole universe opened up for astronomers to study. And so this field, the thing to appreciate about this field is, imagine taking a grain of rice between your thumb and your forefinger, hold it at an arm's length, and hold it up to the sky. Okay, that's about the size of this field of view. And if you were to sit down and count every little point in this image, pretty much every single one of them is a galaxy, you would immediately come up with the number 3,000. Well, all right, not immediately. Maybe it would take you a little while. There are 3,000 galaxies in this tiny field. And then if you calculate how many grains of rice you have to hold up to the full sky, you are left with the fact that there are billions of galaxies in the observable universe, which I just think is astounding. And each galaxy itself contains hundreds of billions of stars. Each star may be surrounded by many planets with moons and with organisms on them that can think and contemplate the observable universe. All right, well, now that we're all on the same page, let's get back to these atoms. The calcium in your bones, for example, the iron in your blood, or the oxygen in the air that you're breathing. This is a cosmic story of epic proportions that spans nearly 14 billion years. And so each individual atom will be a part of your body for as little as a nanosecond to as long as about 30 years. You might be surprised to find out that your atoms are not actually yours. They weren't forged for your exclusive use. And in your body and all over the planet, they're being continually recycled into different forms. These atoms have existed for billions of years and will go on existing for billions more. And perhaps one of my absolute favorite illustrations is this example. Okay, so just put down your beer just for a minute, and everybody take a deep breath with me. Fill up your lungs with as much air as you can. Think about that breath, how much volume there is in it. In that breath full of air, there are at least as many atoms as there are breathfuls of air in the entire Earth's atmosphere. And that means that it's very likely that in that last breath you just drew, it contains at least one atom in common with the first breath you ever drew as a human being on planet Earth. And so just as the atoms in the air that you are breathing have been cycling on planet Earth for its 4.5 billion year history, so have they been cycling for billions of years more on the largest known scales, and they're going to continue to cycle. Okay, so let's start our cosmic origin story at the very beginning, 13.7 billion years ago. And in the very beginning, both space and time and matter were created in a very dramatic event that we call the Big Bang, which was neither big nor did it produce a bang, but that's a subject for a different talk too. When the universe was 3 minutes old, it had expanded and cooled enough for the protons and neutrons to combine into the nuclei of our friends, the atoms. And it was only the lightest and simplest nuclei of hydrogen, helium, lithium, and beryllium, trace amounts of beryllium, that were produced during this time. But the universe was actually still too hot for another 300,000 years for these nuclei to attract their crazy little electrons. So 300,000 years after the Big Bang, these electrons combined with their nuclei, okay? And that allows light to stream freely throughout the universe. And the first picture we can take of the universe is what you see right here. This is from Planck. This is the cosmic microwave background. And it's basically like a baby picture of the universe, and it's around us at all times. Okay, but we're not just made of hydrogen and helium and trace light elements. So how did the other 88 natural elements come about? And so it turns out to understand this, you need to understand fusion and other complex processes that happen in very hot gas. And so most of the most common heavier elements like oxygen form in the cores of massive stars. The carbon in your body likely originated in the first stars to populate the observable universe. And so you've heard the phrase, we are stardust, and that's where this comes from. But that's not the whole story, right? We're not actually inside of stars. Don't you want to know how we get outside of stars? So these first stars, they formed several 100 million years after the Big Bang, which is actually pretty short time. And they're far more luminous and more massive than our own sun. Our own sun is fusing hydrogen into helium, but these massive stars are fusing heavier and heavier elements and fundamentally changed the universe and its evolution. And so inside these massive stars, it's incredibly hot, and atomic nuclei are colliding extremely rapidly. And so to make an oxygen atom, for example, you ram a carbon nucleus with 6 protons and neutrons into a helium nucleus with 2 of each, and boom, this collision happens at such a high speed. You form oxygen, you release a lot of heat, light, energy, and with that energy, you can fuse heavier and heavier elements. And as a result of all of these collisions, it gets hotter and hotter in the core of this star, and you go on to form sulfur, silicon, magnesium. But we don't live inside of stars. Our atoms turn out to have escaped the stars, luckily for us. So after about 1 million years of heating up and fusing heavier and heavier nuclei, the massive star reaches a breaking point. This happens when the energy radiated away with each collision is no longer able to counterbalance the force of gravity, which is pulling everything inward. And the inside of the star begins to collapse on itself at around 25% of the speed of light. And things get so out of balance that there's this huge release of energy that causes the entire star to basically explode and propel its materials outward. And this explosion shockwave sweeps up gaseous material that had surrounded the star and creates a phenomenon that we know as supernova, which creates absolutely beautiful images like the one seen here, taken with the Hubble Space Telescope. And so besides this expanding shell of material, all that's left is a black hole where the star once was. Okay, So now these atoms that are going to become parts of our bodies are now moving rapidly away from the surrounding devastation. As things begin to cool off, they move further and further from that stellar mass black hole. And over the next 100,000 years or so, the atoms will continue to cool down. And actually, fun fact, cooling in astronomy means producing photons, particles of light, which make these beautiful and real images here from the Hubble Space Telescope of nebulae in our own interstellar medium. Anyway, these photons, the atoms, mix with the gas surrounding the site of the supernova and spread over the vast landscapes of clouds known as the interstellar medium. And in this gassy, desolate soup, it's like being on a gigantic galactic merry-go-round with bumps and turbulence, and there's exploding stars everywhere around you. It's not really a friendly environment. Don't be fooled, right? Because galaxies look pretty, but they're actually really violent places. And so being constantly surrounded by these giant explosions, most atoms don't simply remain in the gas of the interstellar medium. Many of them will ultimately be swept up in these huge galaxy-scale winds generated by hundreds of millions of these massive stars, ending their lives with these spectacular and energetic explosions. This is one of my favorite galaxies here, M82, another beautiful image taken with the Hubble Space Telescope in combination with data from the Chandra Telescope, Spitzer Space Telescope. And you can see this material being carried away out of the great spinning, swirling disk of the galaxy into the great space beyond. And I just love this image. And this might be what the Milky Way looked like in its youth, a violent young Milky Way. And so it's now in the space surrounding the galaxy. It's not in the disk anymore. It's in this circumgalactic medium. Maybe it drifts even into the intergalactic medium. It extends to distances greater than 10 times that of the disk. And it turns out that most of the atoms are going to remain here for a couple billion years, traveling between galaxies, exposed to very high radiation levels from distant exploding galaxies. And these are lonely, vast expanses for atoms with less than 1 atom per cubic meter, which is an insanely low density when you think about an atom, right? And it's an unpredictable and very hostile environment. The atoms in your body have survived a lot. All right, so we're not actually drifting around in the intergalactic medium. We live on a planet orbiting a star inside of a galaxy. So how did we end up here? Well, it turns out that's what we're fighting about at this Kavli Institute for Theoretical Physics workshop that Cameron alluded to at the very beginning of the evening. It turns out that the gas outside of a galaxy has to cool down eventually, and it probably falls back down onto the galaxy. It might fall kind of like rain, and this process might be, we call it the galactic fountain. And so all of the atoms that were once outside of a galaxy are now kind of reincorporated into the interstellar medium of a galaxy. And now, once they're back in the interstellar medium, the atoms can yet again get caught in another violent collapse. But this time, the collapse does not destroy a star, it creates one. And so the extent of this new collapse is immense. It's more than a factor of 10 million, that's 7 powers of 10, change in the density from a diffuse cloud of molecules to the young protostar interior. And so during this collapse, collisions between atoms and molecules are happening at higher and higher frequency, and the temperature is rising again. The material goes from minus 433 degrees Fahrenheit to over 1,000,000 degrees Fahrenheit in a short matter of time, around 100,000 years, and the material is spinning faster and faster until it forms a new star. And these atoms that eventually become part of your body, instead of going with the bulk of the material into the star itself, the atoms in your body, the atoms that we breathe and that we eat, all of the atoms on this planet will spin faster and faster in a giant gaseous and dusty debris disk around the forming star, which will eventually become our planet. And this forming star in this illustration is a protosun that existed 5 billion years ago. And in the first 100,000 years of its existence, the nebula surrounding the protosun gets flattened into a spinning, what's called protoplanetary disk. And in this disk, denser and denser particles collide, and the disk will go from dusty to rocky over the course of several million years. And the atoms in our body, they ended up bound to one of these rocks 93 million miles from its central star, which is our sun. And in the billions of years that they have been on our planet Earth, the atoms in your body have been in vast oceans, in the air, breathed by dinosaurs, and they'll continue to be a part of the planet for billions of years more, long after humans have walked the Earth. And so I just want to close by saying that I hope the next day you have a hard day and you go outside, and maybe if you're lucky, you won't see only clouds. You won't be in like Seattle, it won't be raining, but you'll see stars, and you'll think the matter that makes up your physical body is part of a universe that's continually evolving and recycling the material within it into new forms. And you might even feel lucky to be a small part of this vast universe, this self-aware substructure that can perceive itself over a vast range of size scales. And even if it's for just the briefest window, I think being able to do that can actually make you feel very large. Thank you very much.
Excellent presentation, Jess. As always, super stellar. Big picture. Really, really good. Thank you.
Thanks, Cameron.
Zach, feel free to jump back in here as well. We'll take questions from our audience. There were a couple that were asked during the presentation, but people are encouraged to ask more questions in the chat window, and we'll try. I'll ask them of Jess.
Great. Sorry, let me just get my mouse here.
Oh yeah.
End my slideshow. Okay, ready.
A question from Brian Federa. How do we know the structure of atoms and subatomic components if they cannot be seen by even our most powerful microscopes? I guess he's referring to the structure of things on subatomic scales. How do we know that things behave the way we think they behave on subatomic scales? Maybe that was the question. Is that the question, Brian?
Wow.
I think that's the question.
I mean, there are electron microscopes. Like, people have actually seen atomic nuclei through microscopes. Beyond that, I don't know as much about that. But what I will say is that, atomic physics makes predictions for the exact, energy levels of an atom, and people can test for this in the lab. You can, hit an oxygen atom with some energy and watch electrons shift, and they have these discrete energy levels. And the spectra that you see in the universe show these exact same, energies that you expect. So
I think that's it. Things, pretty much all of our models of physics would fall apart if we weren't able to determine the low-level structure of these things. As you point out, the electron structure is like finely tuned and finely tested to these different quantized energy levels and such. So
you could Google like a real picture of an atom. It's pretty cool.
Let's see. More questions. Is the atomic recycling restricted to the galaxy of origin, or is there intergalactic atom sharing?
There's totally intergalactic atom sharing. That is a great question. I love that question. Because yes, so it turns out that people like Zach, these simulators, they run cosmological simulations. Some more than 40% of the recycling material and potentially more comes from other galaxies, like originated inside the stars of other galaxies. And so this material is just being transferred over these huge, vast scales.
Absolutely. What is the proportion of supernova ejecta which is ionized and fails to return to the neutral state before entering low density space?
Whoa. That's a great, I don't think we know the answer to that. I think that there are specialists who simulate this kind of thing. But I will say that most of the gas, when the supernova, explodes, is going to be very hot and very ionized. It's possible that within that, it sweeps up gas from around it, and sometimes really cold, clumpy gas gets swept up and taken out with it. We think also that materials cooling in that wind itself. I don't know the exact proportions, though. I would tell you something wrong if I had to guess.
No, but I mean, that addresses it. And that's one of the topics that we're trying to address during this program, this ongoing physics program that we're all participating in right now, is trying to figure out, how the gas cools, how it pulls other cooler gas with it, and the origin of it. I think Zach may be talking a little bit about this in his presentation. I'm not sure. A little bit.
I switched to my
tiny
martini.
bit maybe, but happy to talk more about it.
Oh yeah, I mean, no pressure. I'm not trying to derail your talk. You've switched to the martini, huh? Now that you're done with the talk, it's
you can ask me the hard questions now.
Okay. Okay. This is again from Brian Federa. How do we know what quarks, for example, look like and how they behave? This is quite far afield, but that's a good question. None of us are strictly particle physicists dealing with the smallest structures in the standard model, so it's hard to address. But so for reference to everyone in the audience, there's the standard model of particle physics, which describes how very, very, very small particles behave. So these are particles on subatomic scales. You've got your hydrogen atom, your helium atom, all your various different elements. And then below that scale, you have your nucleus and electrons orbiting around those nuclei. And the nucleus is composed of protons and neutrons. And then the standard theory dictates that protons and neutrons themselves can be decomposed into different kinds of quarks, up, down, top, bottom, strange, and what's the other one? Charm. Strange.
And so
charm quarks.
You asked how they're observed. It's through particle accelerators, right? Like physicists, there are physicists out there that are building these crazy tunnels underground and slamming atoms together and watching things happen after they slam them together. And I think that they observe quarks in this way. I don't know for sure.
I believe that's correct. Yeah, you get really energetic, for the most part, magnets that use their magnetic fields to send charged particles really, really fast at near the speed of light. You slam them into other particles, and then you see what comes out of the wreckage, and that tends to be the constituent parts like quarks and so on and so forth. Okay, let's see. Another question. Can you explain more in depth about the proof that what we see is gas, including spectroscopy? Further, are there typical relationships between observed redshift and metallicity?
Wow, those are two really interesting questions. First of all, it's not actually gas, it's technically plasma. And this isn't something that you have a ton of experience with, but the reason that we know, most of the atoms are missing their electrons. And the reasons that we know is we can take these very, very high resolution spectra with the Hubble Space Telescope and look at the precise energies at which the light from some background source is absorbed. And you can tell exactly what the nucleus is, how many electrons it has, and exactly what transition the electron made in order to absorb a photon at that exact energy. So you know that you're looking at, a diffuse plasma, and it's predominantly ionized outside of galaxies. There's also neutral gas that you can see too. And there's other transitions that you can see in emission, like, there's hydrogen 21 centimeter, like when an electron randomly decides to flip the way that it's spinning around. And so that's a very low energy transition, and that happens in neutral hydrogen. So you can look at all these things. Now, metallicity and redshift. Okay, so metallicity, here's a good story. I don't know. I told my mom about this. She might be here. She might get to hear this story, but I used to work on metals, okay? And one of my first papers that I ever wrote had a metals in the title. And my parents wanted to read the paper, and so I gave them the paper that I had written in like the astronomical journal, and all about metals. And my mom, after she had finished reading it, she's like, "Oh, that was pretty good. I have one question though." One question. I was like, "Okay, what's the question?" She's like, "Oxygen is a metal?" And that's what she asked. And so everything that's not hydrogen, helium, or these trace light elements like beryllium and lithium is a metal in astronomy. And metallicity just quantifies what fraction of these heavier elements there are relative to hydrogen. And so there are trends that we can observe with metallicity, and they often have to do with the kind of star that ejected it, how old it was, when it formed, the material out of which it formed. So there's lots of trends, and there are trends with redshift. Redshift is further back in time, fewer metals have been produced, so it's lower metallicity.
Very good. A question from Ben Op 99.
Oh gosh, not him. That guy.
What is the average temperature of a baryon in the universe?
Oh, good question, Ben. I mean, obviously, 80% of baryons are outside of galaxies in the intergalactic medium, and they're probably around 1 million degrees.
Yeah, I would agree with that.
Ben, don't ask me questions that you already know the answer to. Gosh.
Okay. I think that's about it. We should probably move on. Oh, yeah, one last question from the Nerdy Walker. Are there any differences in the way in which the heavier elements formed using merging neutron stars? Is there any difference in the way those elements would be recycled through the circumgalactic medium than other elements?
That is a great question. Yes, I'm sure, almost certainly, yes, because the vast majority of the metals that come out of supernovae, and so those will have more of like the stellar composition, but some of those like trace heavy elements that you like exotic heavy elements that you form with neutron star collisions, or in like the shock wave of a supernova, although those will get out anyway. Yes, you could take different ratios of those trace elements, and I bet they would be slightly less out in the circumgalactic medium, but they're so trace, I don't know that we have any actual data to support that.
Ben Op 99 confirmed that it was about 1 million Kelvin, 1 million degrees for the average baryon.
Thanks, Ben. I appreciate the question, Ben. I'm glad you're here, Ben. He's another co-organizer of our Kavli Institute for Theoretical Physics meeting. Ben Op.
Yes. Okay. Let's move on. Thank you very much, Jess. That was excellent. As always, tremendous presentation. Hopefully you'll stick around for our pub trivia in a few moments after we hear from Zach.
I'll be here.
Okay. I'd like to introduce our next speaker, Dr. Zach Hafen. Let's see. What if we live in a simulation? A speculative question you might toss around with friends late at night and a few drinks in. Dr. Zach Hafen is the McHugh Postdoctoral Fellow at the University of California, Irvine, and an astrophysicist who takes this question seriously by building and exploring simulated universes. Alongside his collaborators, he uses these universes to study the cosmic creation of Earth and our host galaxy, the Milky Way. In addition, his cats routinely interrupt serious Zoom conversations on these topics and have been known to stand on his keyboard in just the right way to delete his message drafts. Yes. So Zach, would you like to, I guess I'll just add that both Jess and Zach are scientific collaborators of mine. We've worked together on papers and are working on projects right now even. Zach and I were both committing to a GitHub repository just today. Yeah, they're great scientists and great speakers. So Zach, do you want to share your screen?
I would be happy to. Okay. Appropriately visible?
Looks great.
Great. Okay, so I'll dive right in. And as Cameron alluded to, I happen to have the fortune to collaborate with him and many others at the conference. And the work that I'm sharing today is really built upon countless amounts of work by a wide variety of astrophysicists, many at Caltech, many in the UC system, some at University of Washington, etc. It's an incredibly collaborative effort, and I would not be able to share any of what I'm talking about if it were not for them. Okay, so what am I talking about? Well, I'm going to make this statement here that exploring the universe requires ingenuity. And, well, let's try and figure out how exactly that could be the case. So first, here's an image. This image might be somewhat familiar to you. This image was taken using the New Horizons space probe a couple years back, and it's an image of Pluto. You can tell by that wonderful heart on the side of it. And so with this image, we were able to learn quite a lot about Pluto. Now, I can't tell you, I can't tell you exactly what, but because that is not my specific area of expertise, but I can tell you that it's been a true treasure trove of information. And this image, it took us at minimum 10 years to produce, because that was the time it took to get the spacecraft to Pluto from Earth, moving at about 1/18,000th the speed of light. So I have a question now for you. And this question, I'm going to kind of just let you sit on it for 15 seconds, because that's the delay time between the video and the YouTube live stream, which is, how long would this spacecraft take to get in order to get to the edge of our own galaxy? Would it take maybe another 10 years, 20 years, 1,000 years? I don't know. Well, I do know, but you're going to answer that question for me. And I'm going to wait until I see some of the first answers pop up in chat, and then we'll go. So, and actually, Cameron, can you just read when you hear some of the first answers pop up in chat?
Sure.
Great, thank you. So I don't have to deal with screen switching.
There's a little lag time between when we say something and when it pops up, but yes.
Yeah, well, you said it's 15 seconds, right?
Yeah, so 1,000,000 years.
Okay, good.
100 years.
All good guesses, yep. Okay, I'll go ahead and reveal it now.
1,000 years, 10 million years. Anyway.
It's going to be 500 million years. This assumes, of course, no travel restrictions. You know, we're not having any sort of pandemic restrictions that are going on for intergalactic travel, or interstellar in this case. But it would take 500 million years just to get to the edge of our own galaxy. And that's with some of the fastest spacecraft we have ever launched. To put that in a historical context, the time from some of the very first cave paintings to today is just 20,000 years. In other words, human civilization could rise and fall thousands of times over before we even got a probe to the edge of our own galaxy. This really highlights to me the difficulty with trying to make travel throughout the galaxy and also learning that type of way. Fortunately, there are alternatives. One alternative is to use the light that has reached us to learn more about the universe. And this image here was actually taken by an amateur astrophotographer using a telescope that they set up in their backyard. Their backyard happened to be in an area that didn't have much light pollution, but it allowed them to take this really wonderful image of galaxies. And with much better telescopes, like the Hubble Space Telescope, that Jess is an expert at using, then we get to get even better images, such as this beautiful one of two merging galaxies. Now, there's an alternative. And this alternative is to, instead of going out there and exploring or looking at the light that comes to us, is to create virtual galaxies that look and act like real galaxies, and then to explore those. As for what that looks like, well, I'll show you pretty soon. Before we go that far, I'm going to motivate this just a bit more. Consider a cloud of gas in a distant galaxy. much like the type that Jess was talking about earlier. With a really good telescope, you could find out information like what the cloud is made of. You could also find out some information about where the cloud is and how the cloud is moving, but you won't be able to find out everything you might want to. With a simulated galaxy, you would be able to find out all of this. Now, whether or not you trust it is another matter, but at least you'll have this information to further understand how gas proceeds throughout galaxies. So I've really hyped this up, but now here's a really basic question. Can we actually make simulated galaxies? It's hard enough to just describe what's going on Earth. So how can we possibly make something the size of a galaxy in a simulation, or many galaxies? So I posit that we can, and I'm going to give you the key ingredients for a virtual galaxy. This will consist of what galaxies are made of, how galaxies change over time, and of course, the necessary computational power to do this. Let's go through these bit by bit. So what are galaxies made of? Well, for the purpose of simulating galaxies, the main things you care about are first, gas. Jess talked a lot about gas. It is essential for simulating galaxies and their environment. There's also stars. I mean, this is classically what we think of when we think of galaxies. You better have this. And then there's dark matter. This is, to some extent, you could think of it as the material that pulls all galaxies and holds them together. Dark matter is matter that doesn't collide with itself, as far as we can tell, or gas and stars, but will still act to pull gravitationally on the other galaxies, on the other material. And so that means that we can use that to understand how galaxies form and evolve. And it actually turns out that dark matter is one of the easiest components to understand from this perspective. Okay, what about how galaxies change over time? Well, for this, you basically need a few physical ingredients that are really important. One is gravity. Here is a very simple simulation of a few particles interacting with gravity, by gravity. And so you need to model gravity in your systems. You also need to model gas behavior, in other words, hydrodynamics. This means understanding how gas moves and flows is actually the same field that many mechanical engineers, for example, work on. Or if you want to understand how fish swim, you need to understand gas behavior because you need to understand hydrodynamics and fluids, and a bunch of other details, which I'll get into in a little bit. And Jess alluded to a number of these. So then next, you also have computational power. And these come primarily in two flavors. One, in university computing clusters. And most universities have a computer cluster that is accessible to their researchers. And the other one are external supercomputers run by the government and available at computing centers around the country. So through some combination of these computers, you can get the work done. But it's really important to use supercomputers. If you try to do this with, say, your laptop, it would take, I think last I calculated, at least like 1,000 years or something. It really depends on the simulation you're running, but it would be much longer than I'm willing to wait around for. Maybe you're more patient than I am. So let me summarize. The ingredients for a virtual galaxy are what galaxies are made of, stars, gas, and dark matter, how galaxies change over time, particularly gravity and gas behavior, and the necessary computational power. If you put all these together, then you might get a working virtual galaxy, except you don't. Galaxies made with just these ingredients that I've highlighted don't produce realistic galactic winds, like those seen here with this galaxy. So what do you need? Well, you need more realistic star-galaxy interactions. This realization has come about in recent years. This includes the effect of supernova. Here in this beautiful simulation, you can see the supernova have driven this wind flying out of the galaxy. So the supernova explosions have created these bubbles and this giant galactic wind in this idealized galaxy plane. You also need to include material expelled from the stars. Again, Jess talked about this. You even need to include the very effect of starlight itself on the surroundings in order to figure out how the ionization, the chemical state of the gas has changed, and much, much more. There's almost always, it seems, like one additional ingredient that we forgot about and are finding out is important. So let me go ahead and show you the result of this. These are virtual galaxies created from the FIRE project. On the left-hand side, this is a virtual galaxy. The FIRE project is the collaboration I primarily work with. It's based out of a number of institutions, including Caltech, as well as UC Irvine, UC San Diego, UC Berkeley, Northwestern, and a number of other institutions. And on the right-hand side is a real galaxy. In my opinion, they look, not bad. They look pretty similar, but I'll let you judge for yourself. Okay, so what does this let us explore? So there's a few things. I'm going to just highlight a few tiny pieces of what this can let us explore. First, I'm going to show you a movie. And this movie shows on the left-hand side all that wonderful gas that Jess talked about. And the right-hand side, what we'd actually see with the visible eye. And so first of all, this is occurring over the course of 13 billion years, sped up to happen in a little over 1 minute. That's certainly not something you can do with a telescope. What else? Well, you can do an investigation of all sorts of really exotic, fascinating things. For example, jets produced by black holes. The things that suck everything in, except they don't actually suck everything in, but that's what we think of it as, that instead are shot across the entire length of galaxies. Or cosmic winds from supernova that can contain as much mass as entire galaxies. Or smaller galaxies that orbit around our own, like moons orbiting planets, but turns out usually much messier. You can mock up what this looks like through a telescope and try and compare it to observations. You can even look at weird things like how dark matter at the center of galaxies gets dug out by supernova explosions. And other things, galactic weather, precipitation, unlike anything we've ever heard of, all this exotic phenomena we're able to understand and study because of simulations like these. So I was going to summarize my main point, which is that the size of the universe is so big that you really have to be creative about the exploration. Use great telescopes, come with fantastic idealized simulations and realistic simulations. And because we can create increasingly realistic virtual galaxies, although there's always room for improvement, we can then use those to explore the universe around us. And this is very convenient because now I can do all this while trapped inside the pandemic and still can explore the universe. Okay, I think that's all I have to present.
Excellent. Thank you very much, Zach. Great. And super cool visualizations and such. Jess, you can come back on too. We encourage people in the audience to ask questions in the chat. There are already a handful here. Let's see. Well, the image that you showed before, was that a real photo of galaxies merging, or was it a simulation in the middle of your talk?
Which image? So I showed one that was pretty early on, and it was this really, here, let me go ahead and pull up the slides.
Okay.
I'll share my screen again. Okay. This image here, because if it was this image, this is a real one, which is absolutely stunning in my mind.
Yeah.
The other images, I think actually every still image that I have is of a real galaxy. Anything that's moving is a virtual galaxy. So left is virtual galaxy here. Right is a real galaxy.
Okay.
This
You
is
showed
a
that-
virtual galaxy.
You showed that image of M82, one up. That's the,
Oh, yeah.
M82 again.
Again, it's like a guaranteed you can find. And
That's M82 without the X-rays. That's all Hubble right there. That's H-alpha emission and optical filters. And it's just one of my favorites. I love this galaxy.
It's a really good image. Yeah. Yeah. No, I'm glad I actually had a slightly different version than the one you showed, simply because yours may be better, but then you can see that, this is an evolving understanding of this galaxy over time. So, okay.
Okay. How do you guys discretize galaxies? Presumably in the simulations. I think this is in the simulations. I'm guessing you don't simulate every star, or do you? How many bodies do you typically have in your N bodies of the simulations? And how do you model the gas?
Oh, goodness. We'd love to simulate every star. It would be great to. We don't. Instead, we simulate as many stars as possible, broken down to as small chunks as possible. The modern simulations, so the highest resolution ones, have resolutions spanning from around 100 times that of our own sun to thousands of times that of our own sun. It depends, of course, on the galaxy. For the smaller galaxies, you can afford higher resolution to break things up into smaller chunks because you don't have as much stuff overall. And for the really large galaxies, you can only look at pretty big chunks because you still have so much resources. But then you break it down to hundreds or 1,000 times the mass of our own sun. And you consider chunks of stars together and chunks of gas together. Also, chunks of dark matter together.
We're just getting to the resolution where now we can do individual stars, but only for small galaxies, like dwarf galaxies. I know Andrew Emmerich was able to do this, or was getting to the point of being able to resolve individual stars for like a 10 to the 8 solar mass dwarf galaxy or something like that. But it's slow and it's hard.
That's intense and very computationally expensive. Yes. It's also very interesting. I think the simulators at the conference that we've been talking about get teased all the time about not having high enough resolution to be able to show realistic gas. So, yeah.
There's the question from Laura May. Thanks for sharing these visualizations with us. Now please share the cats.
Oh, there was one that came across my my screen earlier. I don't know. It sounds like my wife is actually going to get up and thrust a cat upon me, so we'll find out.
Is it going to be Crouton?
No, it's going to be Chell. So here we go.
You have a cat named Crouton, though, right?
I have a cat named Crouton. Yes, that's why our cat named Crouton, we named our trivia team after it, and that's why we won. It definitely wasn't because Cameron was incredibly knowledgeable about a wide variety of trivia things.
I looked at the answers in advance.
Yeah. Yep. And then there's Crouton.
Oh, well. Crouton, the famous Crouton. I need to see Crouton. Sorry.
Well, Crouton is known for being a little destructive, so.
Okay. I love Crouton.
He is sweet. And also not going to stay because he's a cat. Chell is, though, so, yeah. Because she's a cat.
A couple of questions. What sort of interesting simulations can one do from a laptop running Python?
Oh, interesting. Okay, so one that you can do that's really fun is you can create just an in-body simulation. Okay, that's a jargon term. You can create a simulation of individual particles moving around with gravity. And so, for example, you could create a simulation of our Earth orbiting the sun and get at a pretty fast speed. Or you can add in additional particles as well and kind of just make your own mess. So that's something that you can do relatively straightforwardly. I actually created an application that should allow one to do that from the web just a while back, just because I felt like it. And there's a number of these online. I think if you probably Google in-body simulation online, you will be able to just pull one up in your browser. I'll give you an example of what.
I can try and find some from colleagues and put them in the Google.
That would be good. Yeah, that would be good. Yeah, because they're really fun to play with.
Yeah.
And you can do some hydrodynamic stuff on your laptop as well. That's the gas behavior stuff. You have to have a little bit of patience, but you can run these codes that are used to create entire galaxies on your laptop. You just have to be much less ambitious.
Yeah, the resolution is, because you and I do this, it's just much coarser in terms of the resolution, so you aren't able to resolve like that cool Kelvin-Helmholtz mixing simulation you showed earlier. You can run that on your laptop at a pretty good resolution and make cool simulations like that with all of these hydro codes for the most part are, well, not all of them. Many of them are open source, so you can download them from Bitbucket or GitHub or whatnot.
Yep.
For instance, Fire, there's a public version of Fire or of Gizmo, which is used to do the fire simulations that we saw. I work on one called Enzo that's open source on I think it's still on Bitbucket, but anyway.
And to just connect this also to technology you might be familiar with, a lot of video games nowadays use hydrodynamics in their graphics. And a lot of them also use ray tracing and light, which is the exact type of kind of physics of understanding how light moves through space that we use oftentimes to make realistic images. So you might already be running some of this on your laptop already. So
there's a question here. How is a galactic wind developed? Ooh, this is a good.
My goodness. Okay.
This is actually the topic of this week's program. How does gas flow out of galaxies? So
it is, yeah. Actually, can I wait till tomorrow morning and then send an answer? Type in Google YouTube chat. Okay. Well, I'll tell you what I know so far. Galactic winds can be developed in a few different ways. So broadly speaking, they can be produced as a result of either supernova feedback, i.e. supernova explosions in galaxies, or black hole feedback, i.e. black holes at the center of galaxies, the really massive ones that will create jets that just go shooting off. And for supernova feedback, the key bit is that you oftentimes seem to need some sort of critical mass of supernova relative to how much gas there is. And it really helps if the supernova is concentrated, for example, as well.
So, well, what's great too is that stars form in clusters, so they do.
Yep, exactly. Yeah, but we're still kind of narrowing down a lot of the details of exactly when you can have galactic winds that will escape the galaxy versus be confined. And that's partially an effect of not just the galaxy itself, but the area around it, because then you can have a whole bunch of gas that's outside the galaxy that the wind would have to push through, for example, which can constrain it.
Okay, I think our last question before we move on to pub trivia. How do you decide on the trade-off between the size, this is going back to the earlier question, the size of the chunks that you include, the size of the particles, the mass of the particles, and obviously the smaller those chunks are, the more expensive it is because there's more of them, but also the trade-off with the realistic representation of a real galaxy by going to smaller, but it's more expensive. Yep. So how do you decide the trade-off?
This is a really good question. And the first answer is that simulators like myself are indecisive. And because of this, there's a large variety of simulations spanning all sorts of different resolutions and sizes. So there's people who work on idealized simulations that get really down to, almost single star areas. And then there's simulations that look at a chunk of a galaxy. Then there's simulations that look at just a single galaxy plane. And then there's ones that look at just a galaxy and its environment. And there's ones that look at just 2 galaxies in their environment. And then there's ones that look at tens of galaxies in their environment. There's all of these different types of simulations. And so the first order answer is we don't decide. We just split up and do different work. But if you want to talk more explicitly about how you might decide for a particular length scale, let's say the galaxy simulations that look at individual galaxies, you want just enough resolution to be able to make sure that, for example, they can resolve star formation in galaxies such that you can have realistic stellar explosions on the level of individual stars, or at least individual clouds of stars. So.
Excellent. Good answer. Yeah, it's hard. We do as expensive, we make them as detailed as we can, but there are limitations on, we're already using like the biggest supercomputers in the world. So there's only so far you can go.
Yep.
Okay, excellent. Thank you both for your wonderful presentations. Really world-class, guys. World-class scientists, world-class presentations. So really great. We will move on and do the second half of Astronomy on Tap, the pub trivia that we encourage everyone, including our speakers, to participate in. So let's see if I can get this going. Can you guys see this? This slide? So for those of you in the audience, you get to participate. You can open up a web browser or go on your phone and go to www.menti.com and then type in this code 7591395, and it should bring up a way of voting on the questions that we have live and interactively, and we'll see your responses here as we step through. There will be 10 questions. A few of them are multi-part. Unfortunately, we don't have a way to track the answers to see who the ultimate winner is, but it's probably for the best because there's always cheaters. There's cheaters in all aspects of life. We request that you not cheat by looking up the answers in Google, but we can't control you. We're not the thought police. So anyway, let's get on with this and see what we've got. Is this going to move forward? Okay. Andromeda. First question. Andromeda is the closest galaxy of similar mass to our Milky Way. Its angular size in the sky is about, and there are, whoa. Okay. Oh yeah, there are 4 options. About the same size as a star, about the same size as the International Space Station, about the same area as the full moon, or bigger than the full moon. So we've got those 4 options, and I'm seeing a live broadcast of you guys as you vote. Right now, bigger than the full moon and the same area as the full moon are tied. Oh, okay. Mixing it up here. Now we've got the same area as the full moon is in the slight lead. Yeah. Well, this is pretty good. People are on the right track. It is definitely on the larger side as opposed to the smaller side. I'm going to step forward and see. The answer is bigger than the full moon. Now, this is a false image. This is a false image produced by the, what's the name of the collaboration that both of you are
Amiga.
Yes. The Amiga collaboration, which has recently put out a couple of studies looking at the galactic atmosphere, much like both Zach and Jess were talking about, this galactic bubble of gas surrounding the Andromeda galaxy. And that's what's represented here in kind of violet colors. So the Andromeda galaxy, you can see by itself, the disk of the galaxy. If you go out in a dark sky site and you know where to look, you can see it. And it is reasonably large. Itself is about 5 times, like the width of the disk is about 5 times the width of the full moon. And then the height of it is about 1 times the full moon. But this region, so that's the white spot in the middle. That's the spot that's a little bit bigger than the full moon. But this purple region is enormous. It's like 3 times the size of the Big Dipper in terms of its width. It's huge because it's this enormous gaseous structure surrounding Andromeda, and it's not that far away.
Cameron, I need to know, why is this image it got 1 thumbs down. Somebody, not a fan, but like the thumbs down are just like flying. There's like 100 of them.
Yeah, I don't know. Menti has this weird thing where it allows people to click on these buttons, and I don't know.
Oh, we got a second thumbs down.
Who thumbs down this type of image? Like, why are you watching then?
People, they hate Andromeda because they know what Andromeda is going to do.
Well, honestly, Andromeda kind of sucks. I actually don't begrudge that person their thumbs down.
I mean, yeah, so to expand on what Cameron said, Andromeda will be colliding with the Milky Way in, I think, 4 to 5 billion years. So it's going to kind of mess us up. So, if you're rooting for the home team, then.
They say when that happens that the residents in the Milky Way are going to have to start calling our galaxy Milkomeda.
Milkomeda. That's right. That's right. Okay, moving to our next question. What telescope recently took such high resolution images of the moon that it could actually resolve features at one of the Apollo landing sites? This actually kind of blew my mind. So this was something I learned in assembling this, this quiz. So feel free to type in whatever telescopes you might know of, space-based, ground-based, optical, the Hubble Space Telescope, a good guess, fine guess. Kepler, another good guess. Keck, good. 17, a fine number. The VLT, the Very Large Telescope, yes, that's a possibility. That's a large ground-based telescope operated by the Europeans in northern Chile. LRO, Lunar Reconnaissance Orbiter, Green Bank, Hubble. These are all good. These are all good guesses. And the answer, someone did get the correct answer. The answer is the Green Bank Telescope. This is a radio. This is the largest steerable radio telescope. It's in West Virginia. And this is essentially, this is to give you some context on what it was able to image. So the way it's operating is they mounted an enormous radar transmitter on the dish so that it sends out radar towards whatever it's pointed at. It bounces off the surface, and then all of the very long baseline array of radio telescopes then observes that reflected radiation and uses interferometry to get extremely high precision. So this is like milli-arc second, sub-milli-arc second precision, like 1,000 times better resolution than you can get from an optical telescope on the ground. And so what is observed here on the left is kind of a zoom in, and you can see where the Apollo 15 landing site is next to the Hadley Rill. And this is actually the image that it was able to take from the ground with this radio. And so the Apollo 15 landing site, I don't know if you can see my cursor, is like right here, which you can marginally resolve. Now, you might think, oh, I'm going to show this to my uncle who believes that the moon landings were a hoax by NASA, and this will show him. But, people are so convinced that you can show them whatever images you want, and they're never going to believe you because they, have such a vested interest in not believing anything that the man, and you're part of the man, tells you. So I wouldn't rely on this. But for those of us who don't believe in a conspiracy theory, a well-disproven conspiracy theory about the veracity of the moon landings, this is a super cool image.
This image is amazing.
Yeah. And they're planning to use this because the Arecibo radio telescope, until it collapsed recently, was used in this capacity for doing radar imaging of different solar system objects. But with its collapse, we lost that capability. So now the Green Bank telescope will be able to do this, and it has a higher power transmitter, so it'll potentially be able to do this better. So I'm super psyched about this. Okay, next question. By both mass and volume, what is the most abundant element in the air we breathe? What do people think about this? I think Jess touched on this in her presentation.
The answer was in my slides.
In her slides, yes.
Mm-hmm.
Whoa, okay, nitrogen, hydrogen, good guesses. Oxygen, yeah, we need that, certainly.
This is interesting. And
okay, I think it's a little bit converged here.
Yeah.
Are
they shifting around because people are answering, or are they shifting around just because?
Every time it votes, I think it shifts around. Every time someone votes and changes the total vote tally, it'll shift around. It's not like I have some weird background animation playing on this thing. Yeah, so people quite correctly guessed nitrogen. Nitrogen makes up the bulk of the air in our atmosphere.
78%.
78%.
Oh wait, which one is it? It's 78% by something and 75% by something. I think it's 75% by mass, 78% by volume.
Okay, yeah, that makes sense. Yeah, exactly. So there's oxygen that we need to breathe, but the nitrogen is the bulk of the stuff there. So good job. All right. Scientists think they've discovered a second Trojan in Earth's orbit. What were Trojans originally discovered around, or like near? What do you guys think? Troy, that is a fair answer. Well done, clever answerer. Saturn, Jupiter, yes. Yes. Asteroid belt. Neptune. I still like Troy. That's really good. All right. Okay. That's clever, but perhaps inappropriate for this audience. Perhaps.
Oh my God.
Let's move on from there. So yeah, the Trojans. The Trojans are a bunch of objects that are a lot like asteroids that are orbiting in the Lagrange points L4 and L5 in the orbit of Jupiter. And we can talk a little bit about what Lagrange points are. So this image, can you guys see my cursor?
No.
Okay. Well, the white circle in the middle is the asteroid belt. Interior to that is the inner solar system. So the Sun, Mercury, Venus, Earth, and Mars. And then the big blue circle on the outside is Jupiter's orbit, and the green objects are the Trojans. So you've got the Greeks that are kind of in front of Jupiter, orbiting at the same rate that Jupiter is, and then you've got the Trojans that are trailing Jupiter. And the reason this happens are something called Lagrange points, which are these locations in a two-body system. In this case, what we're seeing is the Sun and I think that's Earth. And so they're listed L1, L2, L3, L4, L5. L1 and L2 and L3 are all in the line that goes through the two objects, in this case, the Sun and the Earth. And then L4 and L5 you can see are these spots about 60 degrees ahead and behind in the orbit of the object. Now, what's interesting is each of those locations is kind of like a gravitationally neutral spot where things will just kind of sit and hang out in some sort of stable manner. So L2, the one to the right of Earth, is where we're putting the James Webb Space Telescope in, well, hopefully in the next year. And it will sit there. And the cool thing about that is that it's always blocked by the Earth, blocking the light from the Sun. So it always remains in the shade. And it can point, and it's far enough away from the Earth that it can see much of the heavens without having to like slew away from the Earth, which is what Hubble has to do all the time.
Yeah. It's an unstable Lagrange point though, right?
It is, yeah. I believe L1, L2, and L3 are all unstable, and L4 and L5, as you can see from this kind of contour plot of the equipotential like lines, that L4 and L5 are reasonably stable. So L1, L2, and L3 are kind of like if you stand a pencil up on its end, it would be stable, but any kind of perturbation to that is just going to cause it to kind of topple over. Whereas L4 and L5 are kind of like rolling a marble down into a bowl. They'll kind of hang out down there. And that's why you tend to find objects that hang out in that place, like these Trojans that are orbiting around Jupiter. So, but a number of different objects in the solar system have Trojans. And now this discovery was that here's the orbit of this new Trojan that's discovered in the orbit of the Earth. So the blue circle is the orbit of the Earth around the Sun. This is the inner solar system. So you've got Mercury kind of wobbling around in the middle, Venus, the second white circle, and then Earth is the orbit, the third circle out, the orbit, the blue orbit. And you can see Earth just is stable, is set as kind of an enlargement at the bottom of the screen in that blue orbit. And then the orange is Mars. So the green thing on this weird hamburger shaped orbit is this Trojan that we've detected that's kind of hanging out 60 degrees in front of the Earth in its orbit around the Sun. So it's stable for short periods, but in long periods, it'll probably get thrown out of there, but it's kind of cool. So now we have like two Trojans hanging out in the Earth's orbit around the Sun, which is pretty awesome.
I don't know what kind of hamburgers you're eating.
It's a delicious green hamburger, the size of an orbit in the solar system.
Looks like a lima bean.
Yeah, okay. Lima bean's better than hamburger, perhaps. Okay. February is Mars month. What three nations are hoping to arrive at Mars this month? Three separate nations. What do you guys think? Oh, people are just laying it out there. USA, UAE, and China. China in big letters. UAE in big letters. Russia, okay. India.
Mordor.
Mordor. Grand. It's the MSA, the Mordor Space Agency, is very active.
India, China, in one word.
Khan. Spock. Oh yeah, didn't the actor who played Khan, he just died this week. It was a bummer. Sorry, guys. That was like the best Star Trek movie.
Rocky.
Rocky. Okay. Okay. Some good guesses here. Still seems like the three largest are China, USA, and UAE. And that, let's step through them. So yes, the USA Perseverance was launched, in July of last year? And it's set to land on February 18th, only 10 days from now at Jezero Crater. This will be a rover similar to Spirit, Opportunity, Curiosity, some of the other rovers that have been roaming the plains of Mars in the last 10 years. It'll have some different instruments, but yeah, super exciting that it's going to be up there, and it's going to have a helicopter. A helicopter, people. We're going to have a helicopter on another planet, which is just wild. So hopefully that does that. Okay. China, with the Tianwen-1 mission, is set to launch set to take orbit in 2 days. 2 days. Sometime around the day after tomorrow's morning. It should be coming into orbit. It's going to hang out in orbit for a while. It has some imaging equipment to image the surface, and then I believe it's meant to land a lander component that will do some studies on the surface itself. But that isn't for a few months, I believe.
It doesn't have a helicopter.
It doesn't have a helicopter. That's true. And then finally, the United Arab Emirates has the HOPE mission that is supposed to land in less than 12 hours, or not land. It's just going to be in orbit. But it's supposed to arrive in less than 12 hours. And they have all kinds of cool stuff online for being able to track it in real time and follow they're being very transparent about their mission. So pretty exciting. This will be primarily monitoring the atmosphere and the climate on Mars over time to better understand the changes that go on there. So I believe the UAE will be only the 5th nation to have reached Mars. Let's see, USA, China. What are the other two? Presumably Russian Space Agency. Has India done it? Or I guess we'd just say European Space Agency.
I have a confession. I am really bad at any astronomy on scales smaller than solar system or eclipse.
That's okay.
So.
Okay. What kind of radiation, named after a Soviet physicist, is created by charged particles traveling faster than the speed of light? But how can anything travel faster than the speed of light? What do you guys think? What do you think? Cherenkov. Okay. Oh, well, big Cherenkov. Cherenkov.
Very big Cherenkov.
No, I guess. I guess the people are unanimous. Sounds Soviet enough. Cherenkov.
There's also, don't sleep on synchrotron, people.
Synchrotron, yeah, oh, I like that.
Or electromagnetic, although that travels at the speed of light, let's be honest.
Crazy fast radiation, that's the technical.
Yeah. But we have Cherenkov, an alternate spelling. Cherenkov.
Oh, Cherenkov. Okay, yeah, I dig it.
Drago.
Drago.
I
Okay,
think that's the right one.
I think so. Let's discover something and name it Drago.
Drago.
Yeah, I mean, there's like Game of Thrones intonations there. There's also Rocky. Wasn't Victor Drago who's the antagonist in Rocky IV? No, Ivan Drago. His son was Victor Drago in Creed 2. Oh, now I'm talking. I'm hopefully not spoiling things.
Wow.
Okay. Anyway, enough talk of boxing franchises. Cherenkov radiation is correct. So Cherenkov radiation. This is looking at a nuclear reactor, like in the cooling water surrounding a nuclear reactor, and you see that it's kind of bathed in this blue light. That is the Cherenkov radiation. Cherenkov radiation is also what you may have heard of an astronomical observatory called IceCube that sits in Antarctica, where they drop these photomultiplier tubes down into the ice. They like drill and melt holes into the ice that go down like a mile and drop these long chains of photomultiplier tubes to look for signals of light. And the idea is that if you get high speed neutrinos coming from some astronomical source and they come through the ice, maybe one of them will interact with an ice particle and turn into some charged particles, which then are traveling so fast that they break the speed of light in that medium and create this blue light. So that's how IceCube is working. But effectively, let's see if I can demonstrate this. Effectively, it's like a sonic boom in the light in electromagnetic spectrum. And you might ask, I thought nothing could travel faster than the speed of light. And you would be right that nothing is allowed to travel faster than the speed of light in a vacuum. But things can travel faster than the speed of light through solids, through like glass, for instance. That's how we calculate how much stuff, the index of refraction of a substance is like how much light bends or is bent when it refracts through water or glass or some other transparent medium. And the index of refraction is just the ratio of the speed of light in that substance to the speed of light in a vacuum. And so, yeah, light actually travels slower in glass than it does in space or air. And so if you get particles that are traveling faster than that, which physics doesn't say it can't, then you get this kind of sonic boom effect, and it ends up having this kind of blue spectrum, which is kind of cool. Have you guys ever seen it? Have you ever looked at a nuclear reactor? I'd love to see it, but maybe in a safe capacity.
I'd like to see it. Have not.
Yeah. Okay. What else? Oh, see.
Oh.
Good one.
I didn't want to. How long will it take for the Milky Way and the Andromeda galaxies to merge together? We actually kind of talked about this earlier in the quiz, I think after the first question, but that's okay. Lots of good options here. Lots of long time scales. I think the bottom answer is it'll take a long time, but just how long do you think it will?
Could compare it to the length of time that it'll take for our sun to turn into a red giant and expand to where we are now.
Yeah, that's right. Okay, mixing it up. It's not a runaway that the answer is the longest, but it's close to a runaway.
I think it's a runaway.
The answer is indeed 5 billion years, roughly 5 billion years. This is a cool visualization of what the Andromeda galaxy would look like. That's the leftmost object, and then the kind of band is our own Milky Way. So this is, you know, a couple billion years in the future when Andromeda is getting closer, but it hasn't yet merged. But there's a great animation here done by our colleagues. I know Gertina Besla was one of the prime members of this study, and Roland Vandermeerl, I think, was the PI on this. So this is a computer simulation representing Andromeda, the Milky Way, and then the other member of our kind of group of galaxies, the Triangulum galaxy, which is in the upper left. But don't worry about it. It's not doing much. Most of what's going on is the Andromeda galaxy and the Milky Way. So over time, they're getting closer to go closer, and then whoosh, they have their first pass, kind of fling out some stars.
Fun fact though, like none of the stars actually bang into each other, which I think is pretty cool. Like these galaxies are mostly, you know, empty space.
Yeah.
Stars or, you know, interstellar medium, but still.
That's very cool. You can just notice how they pass right through each other, just as Jess was saying. And, you know, there's no saying that maybe there might be some sort of radiation event that happens when they collide, caused by increased gas feeding onto black holes at the center that might cause trouble for us. But we're not going to run into another star. And so therefore, at least for that reason, we won't be wiped out when they're colliding.
I want to be alive in 5 billion years so badly.
Yeah.
So good job. Seems like most people got that one correctly. Nice job, team. Here's an obscure one. What is the largest constellation in the sky? This is kind of a trick question because constellations, yes, constellations intrinsically have size, but for astronomers' purposes, constellations are a bit like the way we draw countries on the surface of the Earth. You know, it's a region on the surface of this sphere, and so constellations represent a region of the sky. And there are 88 different constellations, at least in the Western, you know, official discretization of the sky. And yeah, some are bigger, some are smaller.
A snake one.
Snake one. Well, there's a few snake ones, but that's interesting. Ursa Major, people like Ursa Major, the Big Dipper. Orion, Sagan, not familiar with that. Hydra. I think that was supposed to be Starlink, but now it's Straylink.
I was fascinated by that one. The Big Dropper too. I like that.
The little dipster, the Big Dropper. Yeah, so seems like people are generally getting the correct answer. It's in fact Hydra. There was a Hydra in there that people were getting.
Is that a snake one? Does the snake one count?
It's a snake one. I mean,
It's kind of snaky.
There's Draco, there's Hydra, there's what's the snake charmer? What is the name for that? You're the observational astronomer.
Thanks. No.
Ophiuchus, yeah. Ophiuchus is the snake handler. But yeah, so Hydra is the largest, but it's primarily in the southern hemisphere. You can kind of barely see it on the horizon from this latitude. Like you can see Procyon in Canis Minor from this latitude, but it's kind of it's pretty low on the horizon. So I guess Hydra is just a bit lower. So I think you'd have to be in more tropical climates to be able to see Hydra well, or the southern hemisphere. And then, there's always a Star Wars planetary question. So in Star Wars, what planet is historically home to a warrior people clad in distinctive metal armor featured in a new television series? So what planet? The Hans Solos. The Targaryens. I like that. That's good. That's good. Some Game of Thrones thrown in there. The Trumpsylvania. Oh my gosh. Tana Ewok planet.
What's Star Wars? That's a good one.
Yeah. Yeah.
Metallica.
Oh yeah. 30 Rock.
Krypton.
Some good ones here.
I honestly expected more of a consensus, though.
Yeah, I did too. I mean, everybody loves the TV show.
Oh, now you say, well, I haven't seen that TV show. I don't know Star Wars that well.
I prefer What's Star Wars?
What's Star Wars getting bigger? I feel like people are entering that now.
Yeah, they are.
Which is pretty rad.
Good, as they should. Yeah, so the correct answer is, in fact, Mandalore. The television program is The Mandalorian. It's pretty good. And everybody loves Baby Yoda. I think that's the big thing. Everybody. Ooh, 2 thumbs down, 3 thumbs down. Getting some hate on this. Okay.
Yeah.
What's Star Wars? Seriously.
Yeah, so the Mandalorian follows this dude who's from Mandalore. His whole people are from Mandalore, and they wear this super sweet armor. Anyway, I saw the first season. It was pretty good. I haven't yet seen the second season, but maybe one of these days. All right. Finally, our last question, multiple choice. What are Pluto's moons named after? Pluto, the dwarf planet.
There's a quick response there.
Quick response. Ooh, Shakespearean characters, indeed. Oh, people like death and war.
I mean, Shakespeare's that's about death too. So.
Yeah.
He's pretty dark.
I guess if you want to be peaceful, you got to go for the water-based, but
nobody's choosing water-based though.
He likes water.
no.
Oh, thank you.
I think that was out of pity.
All right. Seems like death-based mythological characters is the favorite. And in fact, yes, it is death-based mythological characters. So Pluto, the Roman god of the underworld, because it's in the outer parts of the solar system where it's dark and cold, kind of like, I guess, some, characterizations of the afterlife might be. And so keeping with that kind of theme, when there were satellites detected orbiting around Pluto, they were all named according to that. So Charon or Charon is the boatman who takes you across the river Styx, which separates the afterlife realm, Pluto's realm, from the rest of us. And let's see, Nyx is the mother of Charon, who's like the goddess of shadows and darkness. And Hydra, we already dealt with, is this many-headed dragon beast. Kerberos is the 3-headed dog who like guards the exit so people can't leave. It's pretty dark. What's cool about this image is seeing that these objects are not spherical, that they deviate from that because, well, on small enough scales, you don't have enough gravitational force to pull you into like a sphere-like object, and these are pretty small. But I guess just as our last thing, since Valentine's Day is coming up, the heart on Valentine's Day, or on Pluto, wishes you happy Valentine's Day, and so do we here at Astronomy on Tap. Anything else you guys want to add?
That was amazing, Cameron.
No,
Thank you very much for hosting us.
Oh, sure. No, glad
Yeah,
to. Glad
that
to.
was really fun.
Yeah. Thank you, viewers, for your participation. And our next one of these will be in a month. in early March, and in late March, we are having an Astronomy on Tap in Mandarin. I will not be hosting. I do not speak Chinese. However, for those of you who do or have friends who do, we encourage you to check it out. I'll have advertisements up for that shortly. It will be done virtually and such over YouTube Live, but with people, scientists in our department and elsewhere who do great science, do great presentations, but also happen to speak Mandarin. So it should be super fun. And yeah, our next stargazing lecture is in 2 weeks, and that should be great as well. So Jess and Zach, as always, excellent presentations. Thanks for being at the top of your game, the top of your scientific fields, and for presenting to us tonight. And thanks everybody for joining us.
That was fun.
It was great.
Bye, everyone. Thanks.
Take care, all.
Okay. We have stopped. I know it's